Welcome to lecture 3 of MCS 507. So MCS 507 is a course in mathematical, statistical, and scientific software. So the purpose of this first week of classes, so this is the third lecture, is to get familiar with Python. And what I plan to do today is to introduce object-oriented programming. Python has the advertisement that it is object-oriented programming done well. Object-oriented programming, what is it? It is bottom-up programming. So last time I introduced functions, or I described functions, and functions can be used to stepwise define, stepwise refine, define as well via functions, stepwise refine a function, refine a main program. So this is, you have a main program and you fill in the functions that are the pieces from the top down. So in object-oriented programming, you work from the bottom, and there is actually no main program. Also the natural context, as you may guess here from the picture of a parabola, one of the main origins of object-oriented programming is in the work of graphical user interfaces. And the main characteristic of a graphical user interface is that the user is driving the action. And the user can be extremely unpredictable, as we all know. So there is no prescribed main program. So there is not really prompting the user, computing something, and then reporting, which is the traditional main top-down view on a program. Okay, I have listed here a formal definition of object-oriented programming. So it's a method of implementation in which programs are organized as cooperative collections of objects. So one defines objects, and actually in particular each of which represents an instance of some class. So there is still a typo here. So let me fix this now. So in some sense I'm doing this with a Jupyter notebook, and I'm working now with a markdown cell. So here is the markdown cell where I have, let me do this again. So you see that I can convert to a raw notebook. So markdown is a very simple way to format text, much simpler than LaTeX, and you can use LaTeX as well. That's the good thing about this, but in essence you see here a list of items, and you just define it as 1, 2, 3, separated by a blank line, and if you want to emphasize something you use the stars. Okay, so sorry for this this interruption. But we've seen that programs are consisting of objects that are collaborating. Each object, what you could do with an object is defined by a class, and an object is an instance of some class. So the third element is that all the classes are members of a hierarchy of classes, united via inheritance relationships. So this definition, and I copied it from the book of Grady Booch. So this definition is complicated, but I mainly want to, I don't want you, I mean, I even don't have memorized this definition, but know that objects, classes, and hierarchies are important. And I hope to illustrate this with one application. That is the definition, that is the modeling of a parabola. So you can see, hopefully, the result, which is a picture of a parabola defined by a point, the focus, and a line. The line is called the directrix. So the parabola consists of all points at equal distance from the focus and its directrix. So that's the geometrical definition of what is a parabola. So on the board behind me, I have indicated where I want to go. I want to show a parabola. So in order to show the parabola, I have to define what is a parabola. So, and what is a parabola? A parabola starts from a focus, a point. So here, the point. So this is at the very, very bottom. So we start with defining a point. And from a point, we have a line. So, and I now realize that I forgot another dependency. So a parabola is defined by a focus and a directrix. So I will start by defining a point, just the coordinates a point in the plane. There's not much to it, and this might seem extremely far-fetched the way we're doing this. But I hope that as we get all the way there, that you start to appreciate the power of the modeling, that you start to realize that programming in this way is actually quite powerful. So to continue the story, so we start here at the bottom of the point, and we want to show something, but instead of immediately going right there, let's show some points. So I will apply the canvas of Tkinter to show points. So as we will see, the class showPoint will extend a point with a canvas. So you can start plotting points. So a line builds on a point. You could say, what is a line? Well, a line starts from a point and a direction. So every line has a direction. So, and I will define the direction with an angle. So a line will take all the properties of a point. We will say it inherits everything from the point, and it adds an angle to this, a direction, where you can go. If that direction is, of course, fixed, the line will actually tell you where you can go. And you can see from the line, we will go to the show line. So everything is very linear and straightforward on this side of the board. So we will just do the same thing as we did with the show point. We will start drawing lines on canvas. To get to the parabola and the show parabola. So showing the parabola, if you would have to do this all the way from scratch, and especially if this is really your first use of Tkinter, this might be a great endeavor, but I will hope to show that there are some difficulties along the way, but we can encapsulate them. So another very important thing in building large programs is that you can encapsulate the complexity of your programs. Okay, so let me start by points in the plane. So that's the first section heading. So we will define a class point. So the point inherits from the object. So there is the keyword class, and point is whatever name I want to give it. And then you see the documentation string, just like a function. And then we have the init. So the init starts with underscore underscore, so 2 underscores. It's not obvious from the layout. It starts with 2 underscores, end with underscores, and then it gives the self. So what is the self? The self refers to the instance of the class. So if you're going to make a point, you call it P, then you want to say what is the first coordinate of P and what is the second coordinate of P. The problem is that the name of the variable, I called it now P, but you can call it X or Y or whatever, although these are not perhaps good names. But the problem is that at the time when you define the constructor, you don't really know what is the name of the instance of the object. While the name by default is self. There's also the other, but we will not get to this. If you want to redefine the operation, suppose that we want to add points, then we would overload the plus operator. And then there is a self, and then there is an other. So, but don't worry about this now. So I will explain what happens when a point is constructed. So what happens when a point is constructed, we take the values of the coordinates, and here by default they are 0. So if the user just wants to make the origin or just any point, then any point, or actually the center point, has coordinates x and y. So what the constructor does, it defines the arguments, what are the values that you want to store in any object of the class. And it also defines, in essence, the data attributes. So the self.xpt and the self.ypt are the 2 data attributes of any instance of the class point. So the string representation is then defined next. So we have seen that any object has a string representation in our first introduction in Python. Well, here you get to define what a point looks like. With the underscore, double underscore string, you are overriding the string method. So you are overriding is a technical word. It mainly means that when the class is defined and you have a point, when you apply the string function to this object, you will actually see what you have defined. So we have taken then the string representation of the coordinates. So that will be different if the coordinates are integers or doubles. So the effect of the dynamic typing is also that the proper string method will be applied to the data attributes. So on return, so the string method always returns a string. And then the last function, which is also the redefinition of representation. So, and this defines the representation. So here I have defined this as the string representation. And you can see that the last line is already written in the setting of how you apply methods to objects. So the self is an object and we apply the string method to it. So the representation will show up if you are in an interactive session and you just type the name of the object. And then typically the representation method is called. This could be different from the string representation, but here we said it the same. So what have we done in this first class definition? We have mainly defined two functions, a constructor and a string representation. So as such, it looks extremely overkill because all what a point will do is store two numbers. So a point, in some sense, it's just a tuple. But the complexity will pay off. So here you see how the point is then being used. So the class point, we make a first point, and the first point is by default the origin. So if we print it, then in the print we are essentially calling the string representation. But I should back up here. When we do the instantiation, when we do first equals point, we call the constructor. We call the underscore init underscore without any arguments. So the x and the y are by default 0, and this shows when we print it. In our second point, we provide coordinates 3 and 4. And then you see that when we print, indeed, we have the x and the y coordinates 3 and 4. Okay, so we have the data, and now we want to draw the points. Well, this is where the show point class comes in. So show point inherits from the class point. So this is why we put point in between round parentheses here. So the class show point will also inherit the data. Now, if we make an instance of the class show point, we must pass the coordinates x and y, by default also 0, and we also pass a canvas. The canvas is C and V. So that's a canvas object. That's an object of Tkinter. So a show point is a point with something added to it, with a canvas where we can draw the point. So notice also the constructor is called. So inside the class show point, we will actually have also a data attribute that is the point. So we make a point there. And the draw method, and the draw method will actually extract the coordinates. So you see here we have the, I need to scroll down. So here you see the draw method now. So the draw method gets the coordinates x, pt, and y, pt, gets the data attributes out there. And then we have the specific, so the canvas is an object itself, and you can create, make a dot. It's actually an oval that is centered at the x and the y coordinate. So what the show point does is, the show point is not in charge of storing the data, but the show point is in charge, what the show point defines is the layout of a data point, how a point will show on canvas. Okay, let me now show how this works. I will print some random points. So I import from Tkinter the tk, and then I import also the canvas. And what I must do is I must remove the window that I had open. So I will execute the next code. I will explain what the next code does. So, but let me execute it. And here you see actually what it does. It prints, it generates 10 random points, and it plots them on canvas. So in the Jupyter interface, there is a window that pops up, and you can see the star. The cell actually keeps running as long as the window remains open. So this is a GUI And the bottom line here, the top.main loop, so top is the instance of a window, of a Tkinter window, with 400 pixels wide and high. That's what the geometry does. So the top main loop listens actually to the user. Now there is no functionality in this GUI. We may, if you're interested, go into graphical user interface development. But for this lecture, I will mainly use the canvas for drawing. And the only action that the user can do is essentially closing the window. Now what happens, so a lot of things are happening. I will define a canvas of 400 pixels wide and high, and the canvas will be put on the window. So that's what the pack does. The pack puts it on the window, and then we generate a list of points. Actually, the points are instances of the class showPoint. So last time I spent some time explaining sharing. Well, here this is an instance of sharing. You may have or may not have been confused by having a canvas as a data attribute. What actually is passed is a reference to a canvas. So all points that are created here have the same canvas. So if I execute the draw, so I first make the list of objects, and then I execute the draw, every point will execute its drawing. Then you see the 10 points, and since the canvas is shared between all the objects, you see that all the points are appearing on the same canvas. So this is another application of sharing data. So the canvas itself is actually an object. So when I make the CNV, CNV is an object of the class canvas. So when I make a canvas, I pass a window, and I pass the dimensions of the canvas. There are also other attributes that can be passed, such as the background color is one of the attributes, but we will not go in there. Okay, so that is points. So points and show point. So in this scheme here, I'm in point and in show point. Let me now go up in the other direction and start to define lines. So what is a line? So we define lines. A line has a point and a direction. So what is also neat is that we can make callable object. So we can start, we will draw the line. So in some sense, I have in the back of the mind that I have to take points on the line. So a callable object is an object that behaves like a function, as I will try to explain. So the direction will be an angle. So, and I will need the sine and the cosine function of the map module. And here you see that the class line inherits from points. So we're going to take again an x and a y coordinate. So we make a point when we construct a line, but then we add an angle to it. So the angle is also by default 0. So by default we will have a horizontal line, starting at the origin and actually going in both directions. Okay, so the string representation, and here you see how you can make more and more complex programs and how you can hide the complexity. So we have already defined what is the string representation of a point. So we don't have to worry about that anymore. The string representation of a line will take the string representation of a point to begin with, and then it will add the angle to it. So this string representation is still good, is only mainly good for viewing. So for parsing, you may perhaps not want this. You may perhaps want another format and not the word angle there, but that can be later changed. So the string representation is used to define the representation. And then comes our callable object. Here you see the overriding of call. So call is a built-in method. So that will determine that if you have an object and the object has name whatever you want it to name, but the name here is self, you will take the coordinates of the point. So the .xpt and the .ypt come from the point. So since the line inherited from the point, it also inherits the data attributes. So the xpt and the ypt were the names of the data attributes that were given when we first made the point. Since the line inherits from the point, it has access to all the data attributes. And it also uses the angle. So we are taking in the direction of the vector. So the angle determines the unit vector, cosine and sine, and we multiply this with a distance. Either we go more than 1 unit distance or we go less, depending whether that argument is 1 or less. See how this is used. So let me execute this. So this is the test. So I have posted also Python programs. So every class defines every file. So we have 6 classes. There are 6 Python scripts. Every file defines a class, so it's good practice to have 1 class per file, although that's not strictly necessary. But why is it good practice? Because with every class you have a test, so there is still a main program there. By the way, this Jupyter notebook is self-contained. I've indicated how Python finds its modules. So you can define somewhere a place where all your classes are defined and then import them in another file or in a cell of a Jupyter notebook. So this is here mainly for the technical purposes, that everything is self-contained in one single Jupyter notebook. As I'm rambling along here, you can see that I first define the default line, which is the horizontal line, and then if you go 5 units farther, you are at the point 50. What is important though is here the callable. So the line is an object that stores data, so the point and the vector, but it also is a function. So by defining the call, you actually make a function from the object. That's also quite cool. So then we can define, say, a vertical line. So a vertical line has angle pi over 2. And here you see the line that starts at 3, 4 and then goes to pi over 4 as the angle. And we can also take points from this. So if you give, of course, argument 0, you get the point, and you can see that if you go straight upwards where 4 units, you add 4 to the point, the y coordinates where you started with. So the checks are made so you can verify just by inspection. Okay, so we are moving up. So we are halfway. So the call was already something special. So let's move on. Let's start drawing lines. And now we arrive at multiple inheritance. So the show line here inherits from line and it inherits from show point. So the show line is actually going to store a point twice. That's kind of a drawback on this design. So we have the line and we have the show point. So the coordinates x and y will actually be stored twice. So the design is not that good. But it's workable. So we have the canvas that is passed, and also the dimension we need. Because here it starts already, we need to know how many pixels wide and high the canvas is in order to draw it properly. And now there is some interesting mathematics that will happen as well. So we have the definition of the class. We always start with the constructor, and then we move on to the string representation. But if you are using the show point, if you are using the canvas, there is no string representation. So the drawing is actually the equivalent to the string representation. It is still short enough. This method still fits in a small cell on a Jupyter notebook. And you see that we draw the point. So this is the benefit of the inheritance. We are inheriting from the show point class, and how the point is represented on canvas is defined there. We don't need to worry about this. We need to worry a little bit on drawing the lines. So we need to compute. So let me first do the specific case, and actually the easiest case is actually the vertical line. So the vertical line, so there is the create line. So I'm now looking at the bottom of this method. So the create line makes a line from the beginning point. So here the XPT0 to the XPD self dimension. So the D was passed as the constructor and stored as dimension. So here you see the self dimension. So the inheritance here, the canvas gets passed to the show point, the angle to the line, and the dimension is actually the new attribute, the new data attribute. So drawing the horizontal line is actually easier, and we do this when the cosine is 0. So if you took numerical analysis, we may have alluded to this. So machine precision is the smallest number you can add to 1 and still make a difference. So what this test does is that if the cosine is less than the machine precision, then you will get into the else case and you will draw the line. Otherwise, what we will do is that we will compute the points where we are intersecting the left and the right bound on canvas. This is where the cosine is used and where we are using the difference from the x coordinates with the width of the canvas. Okay, and I'm realizing now that I'm not explaining this quite correctly. but for the purpose of, so there's some mathematics involved here. So the best way to do this is to sit down, take a piece of paper and really draw it out and see that the formulas work out. But I'm having only 10 minutes left and I have to explain still the parabolas. So let me show actually how this works. So I will draw 10 random lines, actually 11 random lines. I will also draw a vertical line. So we import the uniform distribution, and then I'm running here the script. So I'm again creating a window of 400 wide and 400 high, and you see that there are, if you count, there should be 11 dots, and you see indeed a vertical line there, and then lines that are drawn with the random angles. So the random angles are generated at random between 0 and 2 times pi. So I will not say too much about this. It follows the same pattern as the drawing of all the random points. So we make a list of lines, and actually the lines are instances of show line. We first define all the attributes and then we draw. Okay, so far so good. We are almost there. So now we are at the right of the board. I'm here now at the parabola. The parabola that inherits from the line, and the line inherits from the point. So in a way, I was wrong by drawing this here. So the parabola essentially inherits from the line, not from the point. Okay, the focus is stored as a separate point. That's a design decision here, not to use multiple inheritance. So we did, to avoid the confusion, there is a point in the line. So the point in the line is defined by the first two coordinates, then the angle, and then the coordinates of the focus. So that actually also corresponds more to the geometrical definition of what is a parabola. It's consisting of a focus and a directrix. There is a string representation that relies on the string representation of the point. So that's the first action that is called here. Then we have the string representation of the line, and we use this to build the resulting string that will be returned. Then there is another technicality. How do you take points on the parabola? So we will draw parabolas. So we will have another call method. And you see that now it gets really complicated because we have to solve a linear system of a 2x2 linear system, and that we can solve via Cramer's rule. So there is the difficulty again when we have a discriminant that is less than the machine precision. In that sense, this case is actually handled here in the second part. So in that sense, this creates the point. Otherwise, what we do is that we take a point on the line, and we also take so here is how we sample on. Perhaps I should probably set this at the very beginning. So how do we sample points on a parabola, well, we run along the directrix. So the directrix is a callable object, and as we run through the directrix, we have a point there, and we take the distance of the point with its with also we use also the focus that we are taking. So this is complicated, and I'm now running out of time to explain this properly. But the point is that we are, as complicated as this is, we are inheriting the sampling from the line, which had its own difficulties in case the line was vertical. So we don't need to deal with those issues anymore. Okay, that is the definition of the parabola. And here you see how we can use the parabola. We make an instance defining the line, the coordinates of the directrix, the angle, and then the coordinates of the focus. And then we can start taking points on the parabola. Actually, the parabola was the most complicated thing. The call method in the parabola was the most important thing that we computed. Okay, now comes again the multiple inheritance. So the show parabola inherits from the parabola and the show line. So what this does, it will define how the methods are plotted. So the drawing of the line is defined in the class showLine in that draw method. So that is the first inheritance is obvious. So we inherit from the parabola, where we inherit from the show line to get the drawing done already. So that's the purpose of this multiple inheritance. Some people don't like multiple inheritance because you see there is this duplication again of data, which is essentially not good. But it's not good because here the x and the y's, they are elementary types. It would be a lot better if there were shared references. So then actually it is not such a big deal if shared references are stored. Then there is only one. So I see now the way it could have been fixed would have been, instead of storing the coordinates of the points as numbers, would be to store the coordinates as references. In that sense, there would be only one instance of the numbers there. Okay, how do we draw a parabola? We draw its focus, so that's just drawing of a point in a sense. So here, I'm not, the focus was just a point that was stored in the parabola. And I'm actually not here using the draw method from the point. I could have done this, but here you see why I didn't do this. I want to plot the focus in red. So the focus is really an important point. So it's no longer sky blue, but it is drawn in red. And actually now the drawing of the parabola, so in some sense this is the main program over there. You could say that we do have a main program, but it is defined, the code for it is defined in the draw. So we draw the directrix, so that's the first method. We draw the line, Then we draw the focus, and then we have points that we are drawing in the range. So we are in the range minus 1000, 1000, that looked good empirically. And we sample points of the parabola. So for each, we actually draw the parabola pixel by pixel. If you have taken numerical analysis, you can think of splines, for example, that would be much, much better suited for this. But that would be a completely different project as well. Okay, and I'm now at the last minutes to actually show how we test all this. So that is the picture that I started with. So you see that I always want to get the same picture because I store the seed. So the seed is stored over here. So this looks like this also is a date essentially when I first made this application. We are making the random numbers, but they actually are not random because of this fixed seed. So I will always see the same picture. So you can see that I make an instance of the show parabola and then I draw it. Okay, I hope that this gave somehow the flavor and the power of object-oriented programming. So we can define objects as they really are. And I should say that my motivation for this application was kind of the wrong definition of a parabola. People define a circle as all the points at the same distance of the center. But then when it comes to defining a parabola, people say parabola is y equals a times x squared plus bx plus c. And that's only true when it is a very particular parabola. Here we have a very general parabola. You see how it is neatly drawn with the focus and the directrix. I think that I'm tempted to start playing with this to change the seed and start running different parabolas. Then you can see how robust this is and what a random parabola may look like. That's another topic essentially. But I leave this up to you. I hope this lecture was interesting. This Jupyter notebook will be posted along with 6 files that define the 6 classes that will be posted on the class website. So I thank you for your attention and I will stop the recording now. So this was the 3rd lecture on an overview of Python. This is definitely not enough. We will see more of Python in the next week, but there the focus will be on the NumPy, SciPy, Matplotlib ecosystem. So I will try to explain vectorization, how actually you can write more efficient Python programs by using vectorization.